தினேஷ் சார் ஸ்டார்ட் பண்ணிடலாமா? So good afternoon to one and all present here. யாராவது ஒருத்தர் ரிப்ளை பண்ணலாமே? தேர்ட் இயர் ஸ்டூடெண்ட்ஸ் யாராவது இருக்கீங்களா?
ஹலோ சார்.
தினேஷ் சார்.
சார் கேக்குதுங்களா?
கேக்குது
சார்
கேக்குது.
சொல்லுங்க சார்.
ஸ்டூடெண்ட் தானே?
சார் நான் தினேஷ்குமார் சார், தினேஷ் சார் பேசுறேன். ஒன்றும் ப்ராப்ளம்.
தினேஷ் தானே சார்? ஓகே ஓகே.
என்னை கூப்பிடா சொல்லி கூப்பிட்டுட்டாங்களா, அதான் டக்குன்னு வாங்கி பேசுறது போச்சு.
சரிங்க சார்,
ஒன்றும் ப்ராப்ளம் இல்லை.
ஓகே சார்.
தேங்க்யூ சார்.
நேத்திக்கு அட்டன் பண்ணவங்க யாராவது இருக்கீங்களாப்பா? ஸ்டூடெண்ட்ஸ் யாராவது நேத்தி கிளாஸ் அட்டன் பண்ணவங்க யாராவது இருக்கீங்களா? சரி, ஓகே. இப்போ நம்ம ஒரு 10 மினிட்ஸ் வந்து நேத்திக்கு டிஸ்கஸ் பண்ணதை அப்படியே ரிவைஸ் பண்ணிட்டு இன்னைக்கு பார்ட் என்னவோ அதை கம்ப்ளீட் பண்ணிடலாம். சரிங்களா? So yesterday we discussed a few things. So what is the need of process control, and what are the topics that will be asked in gate examinations. ஸோ அதில் என்னென்ன டாபிக்ஸ்லாம் நம்ம நேற்று கவர் பண்ணோம் அப்படின்னா, we have discussed about we have given a small introduction to Laplace transform. What is Laplace transform, and the definition of Laplace transform, and what are the different input functions or forcing functions அப்படின்னு பார்த்தோம். And then we how to find the Laplace transform of a given function அப்படின்றத பார்த்தோம். Okay. Then we discussed about the transfer functions, what is transfer function, and what are the different forcing functions, like step function, sinusoidal function, ramp. Okay. ஸோ இதெல்லாம் பார்த்தோம். அதுக்கு ஒரு சில எக்ஸாம்பிள்ஸ்லாம் பார்த்தோம். தென் ஆர்டர் ஆஃப் சிஸ்டம், டைம் கான்ஸ்டன்ட். டைம் கான்ஸ்டன்ட்னா என்னன்னு பார்த்தோம். What is time constant, and what is order of a system. We have first order system, second order systems, and it goes on. But usually in industry we deal with only first order and second order system to the maximum extent. Almost all the systems are first order, either first order or second order. if you increase the complexity of the systems, that is by having higher order systems, then it is difficult, or the complexity increases for controlling such systems. Okay. So in UG level, we deal with only first order systems and to some extent second order systems. And when we talk about advanced control systems like cascade or feed forward control or dead time compensation, um, IMC, internal model control, these are some of the advanced control systems where you couple, where you have more than one controller, or you have a forward control systems. Okay. So here, in first order system, we have, I have given you some examples for first order, like mercury thermometer and liquid level system. So and we know what is the transfer function, and the transfer function definition also it is discussed yesterday. Second order systems, similarly, we have given some examples. What are the examples for second order system nu பார்த்தோம், right? And we discussed about a transportation lag and positive and negative feedback system, servo and regulator mechanism பார்த்தோம். Okay. So positive and negative feedback systems என்னன்றது பார்த்தோம். Comparison between positive and negative feedback system. If a signal to a comparator is added, that is signal as a measured value, comparator will give the information to the controller. In turn, it gives signal to the final control element. So the comparator will receive signal from the measuring element. So the measuring element, when it is added to the comparator, it is positive feedback system. And when it is a difference of set point and the measured value, then it is negative feedback system. Almost most of the systems are negative feedback. And we have discussed about a regulator and servo mechanism. Servo is where your set point is constant and you vary the load, and in regulator it is vice versa. Okay, so these are the things that we have discussed yesterday, and we also solved some problems using how to find the Laplace transform of a given function. Also, we given a second order system, how to find the overshoot or decay ratio, the period of oscillation. So these parameters we have calculated using some formulas, right? So rise time something. Now, the next part of your process control deals with the main controllers. Okay. So controller is one major area. As we discussed yesterday, that the ultimate objective of this process control is to design a controller. So why do we need a controller, and what controller actually do, right? So these are the some of the important points that we discussed. There are mainly three different types of controllers: proportional, integral, and derivative controllers. Okay, each have an independent action. Each controller is independent. Okay, proportional, integral, and derivative controllers. So we will discuss these three controllers in brief. Okay. So what actually proportional controller do, and when it is combined with integral and derivative action all together, so how is the controller action, and what are the complexities or problems associated with the controllers, right? So it has some transfer function. The controller has some transfer function, and it has some tuning parameters as well, right? So these are the things that we are going to discuss now. So I'm just going to share my screen. So now I have started sharing my screen. You can see this. So what is PID control? So let's take a step back and define what is control then. Control is just making a dynamic process behave in the way we want, right? So why do we need a control? If a process without a control will just behave in their own way, right? And it can result in disaster. And sometimes, yes, we don't get the desired product as well. So we need to do some of the things to control the process. And here it is said as dynamic process. Dynamic in the way it it changes with time. Dynamic is changing with time, right? So there is a difference between dynamic process and steady state process. Steady state process is one which does not change with respect to time, whereas dynamic process is something which changes with time. Okay, so when we influence, there are some of the ways we are to do this. To influence the process, we can control, that is to influence the process, and we can see how the process behaves, right? And define how we want it to behave, right? So these are some of the ways we can control a process, right? So we usually specify a value we want some output of the system to have, right? So that is called as set point. That is your desired value, right? Set point is your desired value, whatever value that you want to maintain. If I want to maintain the process in such a way that we get a desired value, right? So that is called as set point. For example, I want to maintain the temperature of the room at 18 degrees centigrade. So I just set the temperature to maintain its 18 degree using a remote, AC remote. We have a air conditioner, right? So in the air conditioner, we will set the value as 18 degree, so that the air conditioner will control the room temperature by maintaining the temperature at the set point. So any changes in the temperature in the room will be automatically controlled, right? Or it will bring it to the set point temperature. Similarly, for a level system that we discussed yesterday, tank level controller system we have discussed. So in the same way, what it does it, if you want to maintain the height of the tank, so the flow will adjust in such a way that it always maintain the it always maintained in that way, right? So the value can be fixed or may change with time. So this is what dynamic. When it is steady state, for example, I have a thermometer and I'm measuring the body temperature. Okay. So initially the thermometer will be at some temperature, 30 degree, let's say it's at room temperature. And I'm just measuring the body temperature. Suddenly what happens, the mercury will start to rise because of the difference in temperature. And when the body temperature is higher compared to the room temperature, then definitely the mercury will rise. And this rise in mercury is read in the thermometer bulb with some readings, and it can rise up to a time, and it will not change after that. The state where the value does not change with respect to time is called a steady state. Okay, so in steady state, all the values are constant with respect to time, but it is not the actual condition in an industry. But in reality, it is not the actual situation. We usually do not have the same conditions. Sometimes in the morning, the temperature is very cold, and in the afternoon, it a little bit higher. So when you supply heat, you do not supply the same amount of heat that we supply in the morning and we supply in the afternoon. Okay. In the morning, let's say the temperature of the water is 20 degree or 25 degree, but in the afternoon it can rise up to 35 degree. Okay, so the amount of heat that we supply in the morning and in the afternoon is not equal. So if we have a set point, it does not work. You cannot expect a steady state value in the industry. So it is, all the systems are dynamic in nature. All the systems are dynamic in nature. It keeps on changing. Not only temperature, sometimes flows. Okay, even a flow of a liquid. See, the pump cannot discharge a constant flow always. It depends on the conditions of the. It can vary depending on many factors, like the friction factor and the velocity difference. Okay, so you cannot expect a pump to deliver the flow at a constant rate. Okay, it depends on several factors. In the same way, other parameters may also change in the process. So all the process are not steady state. It is dynamic in nature. So that's why we need a control system. Okay. So how do we influence the process? We need some kind of control input, right? We need some input, and we can create some changes in the behavior of the process. See, for example, how do I heat? How do I control the boiling of a liquid by supplying more amount of heat? See, uh, in our home, we used to heat milk, right? So we adjust the knob of the gas stove to increase the flame or to decrease the flame. So depending upon the boiling condition of the milk, right? When the milk boils, and we usually reduce the flame, right? So by intuition we know that the milk is going to boil and we have to reduce the heat. So by in such a way that the control input is given. So we need to create a changes in the behavior of the process. It can be a heater or a valve or a pump. Okay, so this is the way we influence the process. So how do we observe the behavior? We know how the process work. We would also know what the output would be for a given control input. See, uh, the same example I will give. We know, இப்போ நம்ம அந்த நாபை வந்து கேஸ் ஸ்டவ்ல அந்த நாபை வந்து இன்க்ரீஸ் பண்றோம் அப்படின்னா பால் பொங்குமா, எவ்வளோ வச்சா பொங்கும் அப்படிங்கிறது நமக்கு தெரியும். இவ்வளோ ஹீட் கொடுத்தா டக்குன்னு இது பொங்கிரும். ஓகே, ஸோ அதுக்கேற்ற மாதிரி ஹீட்டை அட்ஜஸ்ட் பண்ணணும் அப்படிங்கிறது நமக்கு தெரியும். right? So most of the time we do not know exactly. We need to measure what the process does. Okay, so what we do is we have to measure. It is called as measured value, or it is called as process variable. So how much of input has to be given in order to get a desired output has to be known. Okay, that is what a control system, control input has to be designed, right? So if you have any, if you want to interrupt at any time, you can ask me questions. Okay, fine. So consider this example. Yesterday also we have discussed this. Here you can see a kiln house where you supply some using some heating element. You are supplying the heat, right? And there is some gas system that is going through the pipe. We are supplying some gas to for ignition, right? There is a temperature gauge here to measure the temperature inside the room. And here there is an operator who is watching the temperature using the temperature gauge, and he will adjust the amount of gas that is to be supplied. So this is your process. Actually, this is your process. The process has to be, the process is something, um, it can be any process, right? Heating process. And we heat by using some flue gas, some gases, right? ஸோ இப்போ என்ன பண்ணுறாங்க இவங்க, இங்கே வந்து பார்த்தீங்கன்னா இந்த டெம்பரேச்சரை பொறுத்து இவங்க இந்த ஹேண்ட் வால்வை வந்து அட்ஜஸ்ட் பண்ணுறோம். ஹேண்ட் வால்வை அட்ஜஸ்ட் பண்ணும்போது அதுக்கேற்ற மாதிரி உனக்கு வந்து the amount of gas will be released. So depending on that, if the temperature is increasing, then he will definitely close the valve. And if the temperature is lower, then definitely he will increase the amount of gas supply. So it actually, it is a feedback control system, right? It is a closed loop. The man, the operator, he's seeing the monitoring the temperature, and he is taking action. So it is a feedback control. Okay, based on the measurement, based on the measured value, he is taking action. But however, this is a feedback control, but it is not a automatic system, right? If you want to replace that operator, we need a controller. The controller has to, I want to replace this operator. It is a manual control. I want to replace this operator so that something will control this whole process. So I need a controller. In the place of operator, I'm just replacing a controller so that the controller will monitor the change in temperature. Okay, and it will execute some plans to control the heating range. So this is what a feedback control system is, right? So controller itself is a system. Controller, we can consider controller itself as a system. And here the input for a controller is your set point and measured value. Okay, for a controller, your input signals are your set point and measured value. See, you can consider the same example. Here you assume this operator as a controller. You assume this operator as a controller. So here the operator actually monitor the temperature in the gauge, and he, using his hand, he is adjusting the valve so that the flow of the gas is controlled. So what the operator is doing is, if you see, let's say the temperature is set at some value, he know at that value it has to be maintained. So he will definitely act accordingly to the changes in temperature and he will adjust the valve. Okay, in the same way, the controller has to take action in such a way that it is maintained at the set point. Okay, the set point is our desired value. So my intention is to maintain the temperature at 50 degrees centigrade. So I'm setting the value at 50 degrees centigrade. But the measured value says it is at 55 degrees centigrade. So it means that there is some error. There is some 5 degrees error because it is higher than the set point value. The excess amount of heat was supplied. Because of that, the measured value has exceeded the set point value. It has to be detected by the controller, and that error has to be compensated. That 5 degree of heat has to be compensated. So the controller has to give a signal in such a way that the final control element can be a valve or a transformer in case of electrical systems. It is adjusted and the temperature is maintained, right? So for a controller, the input signals are your set point and measured value, whereas your output is your control signal. Output from the controller is your control signal, right? So continuing that, like the controller needs to convert two signals of one physical quantity into one signal of other, right? Let's say temperature is your uh, one set point. Okay, this has to be converted into another signal. The controller has to convert that quantity, physical quantity, as a signal. Okay, and that signal, based on that signal, the final control element is adjusted. In the case, it is a valve. You see, in this case, it is a valve, right? So here set point is your temperature. That is your physical quantity. If it receives the controller receives the signal, and it converts the signal into another form, and it has to be given to the final control element, right? So we know that the process is dynamic system. Its output depend on current inputs as well as its past state. For the controller to deal with this, it makes sense that it should be a dynamic system too. Okay, so as I said, uh, if it is a dynamic system, then the controller action is required. Usually, a steady state system does not require a controller. And outputs depend on current inputs as well as its past state. It means that error is also a function of time. Error is also a function of time. See, error, what is error? Error is nothing but the difference of your set point and measured value. And it can change with respect to time. Error cannot be a constant function. If it is a constant function, if the error is zero, then the controller output will be zero. The controller will not take any action unless the error is non-zero. So for the controller to deal with this, it makes sense that it should be a dynamic system for the controller to act. As I said, the error signal, um, very often we can think of a controller acting on the difference between set point and measured value. He's here. You see here the control. This is your controller. Okay, and set point is one input already given to the controller, and we have another input, that is your measured value, and this comparator will compare both the values, this set point and measured value. Suppose here set point is 50 degrees centigrade and your measured value is 40 degrees centigrade. This comparator will compare both the values. 50 minus 40 will give you some error 10 degrees centigrade. This 10 degrees centigrade is sent to the controller. And this controller, based on the error, will give some output signal. This controller will actually control the system. It produces some output signal, and based on the output signal, the final control element can be adjusted. See, final control element is nothing but one which executes the plan. I mean, if a controller gives some plan, the final control element will execute it, right? If I want to adjust the valve to this position, if the control valve has to be adjusted to some position, the controller will give the signal and in such a way that the control valve is adjusted. Okay, and it has to be a closed loop. You see, this is your actual process, and from the process you measure the value and you give it to the comparator, and the comparator will compare point and it produces some error, and this error is the input to the controller, and the controller will produce some signal, that is u, that is your controller output, and it goes to the process. Okay, so this is what we have seen yesterday, the feedback loop. Okay, எதுக்கு ஒன்று பார்த்தோம், நம்ம ஃபீட்பேக் சிஸ்டம் அப்படின்னு ஒன்று பார்த்தோம். அதில் நான் மேஜர் பார்ட்ஸ் ஆஃப் அ கண்ட்ரோல் சிஸ்டம் என்னென்னு சொன்னேன். ரிமெம்பர், வாட் ஆர் த மேஜர் பார்ட்ஸ் ஆஃப் அ கண்ட்ரோல் சிஸ்டம்? We have process, measuring element, controller, and final control element. These are the four major parts of a control system. Okay. So what is this dynamic controller? The controller cannot be ideal. That means a controller cannot take action based on a single information. If it takes action based on a present situation, then we cannot predict what happens in the future. I mean, the future in the sense, if a current value கான error, current error வேல்யூக்கு மட்டும் நீ ஒரு கண்ட்ரோலர் ஆக்ஷன் எடுத்துச்சு அப்படின்னா, error is a function of time, as I said. Okay, the error keeps on changing. The error may be different in another 1 hour. And if a controller take action to that condition alone, then the control is not achieved. Okay, so we usually think of time. One is present, past, and future, right? So the controller has to be a dynamic one. It has to look after the present, past, and future. Accordingly, it has to take action. So we have to design a controller in such a way that it should take into account the present values, past values, and predict the future values. So combination of such kind of controllers is essential in controlling the process. A combination of these three actions is required in order to achieve the control and the control has to be quick and accurate. So we can split the controller in three parts. One is present, past, and future. Okay. So three modes of are present in a PID controller. As I said, proportional, integral, and derivative controller. There are three. These are three individual modes of control. Okay. So proportional action, integral action, and derivative action. So what is proportional, what is integral, and what is derivative? We will see individually. Okay. So this part of a controller is only concerned with what the error is, what is the present error. Okay, at that time, what is the error? And the control signal will be proportional to that error. Let U be the control signal. Use your will be based on the error that is proportional to the error. Here you can see U proportional to error. So if you remove this proportionality constant, you will have a proportionality constant that is Kp. That is your gain, proportional gain. So your U will be a value which is equal to Kp into E. E is nothing but error and Kp is nothing but your proportional gain. Okay, so proportional controller is something which produces a signal which is proportional to that error. That control signal will be proportional to that error. So how it actually looks? The control action at any instant is same as a constant times the error at the same instant. Okay, for example, if I replace here, the present is your proportional controller because the proportional controller will take action at that particular time for a particular error value at the present time. So here the present value is replaced with the proportional controller. How does your proportional controller work? It actually produces a signal which is proportional to the error. Kp into E is your output signal for a proportional controller. You can think, see, let's say if a reactor is maintained at 50 degrees centigrade, you are maintaining that temperature by using some by heating, electrical heating or something like that. Okay, so if the temperature is, I'm setting the value at 50 degrees centigrade, and the controller will check whether the reactor temperature is maintained at that value. If the reactor temperature is decreased, what happens? This controller will produce some signal, and based on that signal, the controller, the final control element will adjust the uh, either it will increase or decrease the flow of the gas, or it will adjust the transformer. So this is proportional. The action is proportional to the error. பட் வி கேன் சி, இப்போ ஒரு 10 டிகிரி வந்து கம்மியாக இருக்குது அப்படின்னா அந்த 10 டிகிரி அட்ஜஸ்ட் பண்ணுறதுக்கு எவ்வளோ ஹீட் தேவைப்படுமோ அதை அந்த கண்ட்ரோலர் வந்து அட்ஜஸ்ட் பண்ணி கொடுக்கும். ஸோ இந்த கண்ட்ரோலை பார்க்கும் போது உங்களுக்கு வந்து ஓகே திஸ் ஆக்ஷன் இஸ் எனஃப் அப்படின்னு தோணும். ஓகே, இஸ் ப்ரொபோர்ஷனல் கண்ட்ரோல் இஸ் எனஃப். Intuitively, it seems like it should be fine on its own. But when the error is big, the control input is also big. As the error is reduced, the control input is also reduced. So a proportional control will take action proportional to that error. If the error is big, then the control output is also big. If the error is small, the control action is also small. It just actually control proportional to the error. But there are some problems associated with that. We'll see what happens. Here you can consider an example. It is a liquid level system. You are maintaining the level of the tank liquid. Okay. So some amount of liquid is entering here, and this is your control valve here, and we are constantly draining the water through another valve. Okay. So this is your inlet valve, and there is an outlet valve here. In the inlet, you have a control valve, right? In the inlet, you have a control valve, and in outlet, you do not have a control valve. I want to maintain the height of the tank. I want to maintain the height of the tank. See, if I want to maintain the height at same position, I cannot change the output flow rate. The output flow rate has to be a constant one. If I change the output flow rate, then height will automatically change. If I want to maintain the height of the tank, then there must be some control action in such a way that it always maintain the same height. The problem with the proportional controller is it produces a steady state error. It produces a steady state error. What is steady state error? Maybe, see, steady state itself is not changing. Then it combines with another term called error, steady state error. So error is constant. In proportional controller, in using proportional controller, we arrive with a steady state error in some places. For example, if the level is maintained at 5 meter, level of the liquid is maintained at 5 meter, maintaining the level at 4.5 meter is not a big problem, but in very complex systems, even a slight variation in the properties may result in uh, spoiling of the quality of the product. Okay, so we cannot encourage that. In such systems, we need accurate control. So proportional controller usually produces a offset. What is the difference between offset and error? Error is nothing but the difference between set point and measured value. Error is nothing but the difference between your set point and measured value, whereas your offset is nothing but the difference between original steady state and a new steady state. See, error is a function of time. If it is if the error keeps on changing, for example 48, 49, 47, 51, 52, if the error keep on changing with respect to, if the error value keep on changing with respect to time, then the error itself is not at steady state. But let me assume a condition where Your set point is 50, but your error value is 45 and it is maintaining at 45. Then what's wrong? It's the error is not changing with respect to time, right? But does it achieve the steady state value? I mean, it has. Does it uh, set to the set point value? No, it has deviated from the set value, but it is maintaining at some constant point, which is not accepted. I want the system to be at 50, but the system has deviated from that value and it has set at 45. But it is maintaining at 45. Still, it is not acceptable. Okay, so with proportional controller, we always have offset, or let us call as steady state error. So proportional controller will have a offset. Proportional, using only proportional action, will have a steady state error. Okay, so you can see here with proportional controller, once the error has reached a value where your kp, see here, this, you can see this level that is going down. What happens? I want to maintain this level, but increasing the flow rate, it has reduced the level of the tank. Then what I have to do is I want to maintain a constant flow in. Okay, if there is a varying flow rate, then definitely the height will vary. Okay, and it will lead to some other position that is called as steady state error. So in that condition, we can summarize that P control, proportional control cannot give a non-zero value of the control at zero error for some types of processes. Okay, so how can we avoid this? Solving this proportional controls problem, how can we get rid of the steady state error? Now what we have to do is, let's ignore the present for the moment and concentrate on what has happened in the past. Okay, we have to look the past values of the control system, because proportional controller will take the present values. The past values has to be taken into account. So now we have to add one more action. We have to add one more action, that is your integral control. Now we have the controller only with proportional control. Now we are going to add one more action to it, that is your integral action, which actually collects the past values. So how does it do? Let's say we can examine how the controller error has evolved in the past. If we sum up the past values of the error, we can get a value that increases when there is a constant error. Okay, so integral is nothing but, see, integration is just nothing but adding the summation. Integration is nothing but summation of the values. So based on the past error values, here you can see in this graph, there is an oscillation. So it shows there is some oscillation in the values. These are some errors. So these are the errors in the past. What this integral action will do is it will sum up the past values of the error. Based on the summation, it will increase, it will produce another output signal in such a way that the past error values are rectified. See, நான் என்ன பண்ணுவேன், இப்போ என்னோட லெவல் வந்து கண்ட்ரோல்னா இப்போ ஒரு எரர் சிக்னல் ப்ரொடியூஸ் பண்ணுது. அந்த எரர் சிக்னல் வந்து ஒரு 5 மீட் ஒரு வேல்யூ எக்ஸ் வேல்யூல இருக்கு. இப்போ என்ன பண்ணும், அந்த எரருக்கு அந்த எக்ஸ் வேல்யூக்கு தான் அந்த கண்ட்ரோலர் வந்து ஆக்ஷன் எடுத்துட்டு இருக்கும். அந்த எக்ஸ் வேல்யூக்கு ஆக்ஷன் எடுக்கிறதுக்கு முன்னாடி என்ன ஆகும்னா, வேற எரர் சேஞ்ச் ஆயிரும். அப்ப அந்த எக்ஸ் வேல்யூக்கு அந்த ஆக்ஷன் எடுக்கிறதுக்குள்ள உனக்கு வந்து வேற ஒரு வேல்யூ சேஞ்ச் ஆயிடுச்சு. Okay, so the error keeps on changing. If a controller takes action to one value, to that value, present value, there is a change in another value. So அப்ப என்ன ஆகுது, control action எடுக்க முடியாம போயிடுது. So that's why what the integral action will do is that it will sum up the past values of the error and we can get a value that increases when there is a constant error. So how do the integral action works? We can let the control be given by sum of the past values of the error scaled by some gain. The sum of the integral, the output there in proportional control, u is equal to kp into e. That is your error signal, your control signal will be proportional to the error value. But here you see your error value is integrated over the time 0 to t. So to a period of time, your error value is integrated and then it is multiplied with some constant value ki. There it is your proportional gain and here it is your integral value. Kp is your proportional gain and here ki refers to integral gain, integral constant. Okay, so there you have only one parameter, that is kp, but here there is another value called tau, it is added. So what this integral action do, it will integrate the past values of the error and it will give signals, right? Okay, then we'll also have another condition. We have an integral gain ki which converts an integrated error to a control signal. We would actually like to parameterize this as a time, as is how fast we can remove a steady state error. Now this integral action will remove the offset. How fast it can do that? It is a big question then, because it actually take the past values and integrate and give the control signal. How fast it can, the control action will be implemented is another question. So that future values has to be taken into account. Okay, so let's rewrite this as u is equal to ki 0 to t e tau into d tau. This is our proportional gain and ti is your integral time, right? So actually it looks like this. When you add this proportional controller and integral controller, you will have this equation. U is equal to kp et e of t plus kp by tau I 0 to t e of tau d tau. So this is your integral and proportional action. So now we have added the integral controller also. And now we have another problem, that how fast or how quick the steady state error is removed. Okay, We solve the steady state error by adding an integral action. That is by doing the past, summing the past values. How can we solve the oscillation problem? It produces more oscillation. When integral action is used, it produces more oscillation. So how do we reduce that oscillation? Is another. So how to solve these oscillations? How do we predict the future of the error? எரர் இப்படி தான் வரும் அப்படின்றத ப்ரெடிக்ட் பண்ணி அதுக்கேற்ற மாதிரி கொடுக்கறது தான் வந்து டெரிவேட்டிவ் ஆக்ஷனோட வேல்யூ. If the gradient of the error is in a direction that makes the error smaller, we can reduce the control input. You see, இந்த எரர் வந்து இந்த இந்த டைரக்ஷன்ல வரலாம், ஐ மீன் இந்த இந்த பேட்டர்ன்ல இருக்கலாம் அப்படின்றத ப்ரெடிக்ட் பண்ணிட்டு அதுக்கேற்ற மாதிரி உங்களுக்கு எரரை வந்து control input reduce பண்ணிக்கலாம். Okay, for example, here you see this damping. It can be easier to think of this as damping. Sometimes something that resists velocity. Think of the wheel on your car. Here you see, in your when you travel in a car, this damping will reduce the velocity of the car. Okay, the suspension. So this will be a hindrance to the speed, right? So how quick it is recovered, how quick it is, the damping is eliminated. That is one of the problem. So there we have a derivative action which actually eliminates this oscillation. See, proportional controller will give an offset, and this offset will be eliminated by the integral action. However, the integral action will produce some oscillation, and this can be eliminated by a derivative action. Again, we have to look what is this derivative action. So it will predict the future values, right? It will predict the future values and it will give the controller output according to it. Okay. So this is your integral part, this is your proportional part, this is your integral part, and this is your derivative part. So when these three actions are combined, then the process will become complex, and we have three tuning parameters. One is Kp, tau I, and tau d, integral time and derivative time parameter. However, your process, the control will be quick and it will be accurate. And it also depends on situation where we have to use integral action and where we have to use the derivative action, or we can use the proportional alone, or we can combine with integral action or derivative action. It depends on the situation and type of application, type of process we use. Okay, by experience we will decide. And some of the problems that are associated with this derivative action is that we know that the derivative is something differentiation. Okay, integration, now it is differentiation. Differentiation, what it does is it amplifies the changes, and also we can get some problems if the measured variable is noisy. See, one example I can give you is that if you want to measure the level of the petrol inside the petrol tank, you will place a level sensor inside the petrol tank. But the situation is the petrol level keeps on fluctuating. It produces some noises to the sensor because we are riding the bike and the level of the petrol keeps on changing, fluctuating, and it produces noises to the sensor. It cannot it cannot give you a accurate value. You understand? It cannot give you a accurate value. So that's why we have to use a filter pass to reduce the noises. In audio systems also we use this amplifier which actually amplifies the signal, enlarge or magnify the signals. If you want to enlarge the noise sounds, we use some amplifier, right? In the same way, when this derivative action will amplifies the changes and it enlarges, magnifies. Also, the other problem that is associated with derivative action is that when the error is constant, then it assumes when you differentiate a constant value, then it becomes zero, and the controller thinks that there is no error and it will not take action. So that's why you see proportional controller can be used alone, and integral controller can be used alone, and derivative action cannot be used alone. The reason being, when error value is differentiated, it becomes zero. Then the controller will assume that there is no error and the control is not achieved. So that's why either the derivative is coupled with integral or the proportional actions. Okay. So we have derivative with filter. We To reduce the noises, we allow this. So this is how a full proportional integral derivative equation looks like. U of S is your controller output. Kp into E of S. Kp is your proportional gain. E of S is your error signal. So this first part is your proportional controller. Then we have added your integral part. Integral part actually sum up the past values of the error. Okay. And integral action actually eliminates the offset, but it produces oscillations. So that is the drawback of this integral action. So to avoid that, we introduce a derivative controller along with PI controller. So this derivative part will actually include the future values also. Okay, includes the future values, predicts the future values, and eliminate or quick the process, speed up the process. So here we are just adding a differential part. So this will look as a complete equation. So when you the motivation for addition of integral and derivative controlled modes is now clear, that when you have proportional alone proportional action alone, then you will end up with offset values. Offset is nothing. Offset is an undesired value. It is not a desired value, because offset is different from error. However, it is not desired value. Error is the difference of set point and measured value, and offset is a difference of original steady state value and the new steady state value. Error is a function of time. It keeps on changing with respect to time. But when the error itself is a constant, then the system is not at a set point value. So that is not needed. So, but in some situation where you do not want to make your system complex, by adding more number of action, different controller action, you will end up with different tuning parameters, and it is increasing the complexity to solve to control the system. So that's why in some situation where 22% of tolerance is allowed, see, there is nothing going to happen if I maintain the level of the tank at 25-meter or 23-meter. It doesn't make a huge difference, right? So there you can allow some tolerance or error limit. But in situations where, like a reactor or a nuclear reactor, something like that, a small change in the property can result in disaster. So there we cannot have that relaxation. So the control should act quickly, and it has to be more accurate. We cannot have a tolerance or relaxation in that kind of situation. So PID controller, proportional, integral, and derivative action put together will bring the process. Controller will work accurately and bring the process quick to the steady state value. Okay, so it is up to the control engineer to decide what modes of control action has to be used according to the situation. So this is the controller part. If you have any doubts on this, you can ask. Also, uh, stability is one topic where you have to concentrate. See, to the maximum extent, we have discussed what are the main things, main topics in the control system. But the restriction of time, I will give you some topics where you have to concentrate for your gate exams. You have to look for stability, Bode plot, how to find the stability of the system. There are several tools used to find the stability of the system. One is Nyquist plot, and another one is Bode plot. These are some of the Ruth criterion. Okay, so these are some of the ways where you can find the stability of the system. Also, you have to look for advanced control systems such as uh, cascade control, feed forward control, and internal model control, dead time compensation. Okay, so feed forward and feedback, feed forward and feedback control are different. Feedback control, actually what it does is it takes action once the error has happened. Whereas feed forward control, actually, it takes action before it should happen. So with this, our topic is completed, and all the best for your GATE exams. Thank you.